Okay, so what we're going to look at this afternoon is we've got several sheets here that take us through key ideas in organic chemistry. So we're not thinking now about the particular groups like alkanes, alcohols, or anything like that. This is ideas in terms of reactions. Okay, and I think we probably need to just start with a bit of a reminder about reactions. So this first sheet is really sort of going to guide us through which bits of a molecule might react, why, and what those mechanisms might be. The other side of that sheet takes us through reactive sites, because obviously if you've got a large molecule involved in a reaction, it's not the whole molecule that's reacting. We've met things like, we've met functional groups, for example, and functional groups are where reactions take place, not the rest of the molecule. So you could have, a huge alcohol molecule, let's say, you've got decanol in your assignment with 10 carbons in it. Those 10 carbons and their attached hydrogens are not the bits that react. It's the bit on the end with the OH group that reacts. So reactive sites, functional groups bit. Types of reagents and then types of reactions. So we will look at some of those. And then there are, there's a bit about drawing mechanisms, and this is where curly arrows come in. And I've taken several bits from Chem Guide to sort of get us through this. And then several sides, 2 sides actually. I know it's stapled strangely, but it's because of the first side. There are several examples of reaction mechanism, so homolytic substitution, homolytic addition, heterolytic electrophilic substitution, heterolytic electrophilic addition. We're not doing all of those. We will do the homolytic substitution, I think, and the heterolytic electrophilic addition. All right, and then the thing on the back is just there to scare the heck out of anybody going to do a chemistry degree. All right, because that's what you have to know, basically. Oh, that's only a bit. I mean, that's organic reaction mechanisms. Yes, yeah. That's what chemistry is really about on the back there. All right. All right. Just as a reminder, what you need to be clear about before we can do this is a bit on atomic structure. Now, I know that's going right back to September, but, it's amazing how easy it is to forget. So if we were to take a carbon atom, for example, all right, how would we draw a carbon atom? What's in the middle? All right, but what particles are in the middle of a carbon atom? Protons and neutrons. How many protons? And on average, how many neutrons? Yeah. And then around that, we've got our electrons. So the first shell contains 2. And the second shell contains, right. Okay. Let's just stick them anywhere for now. Okay, that's a good starting point. So we know that our carbon atoms have got 4 electrons on the outside. I seem to remember drawing it wrong last week. Because I was drawing a Lewis structure, wasn't I? And I actually put 6 around the outside. So there's our carbon. All right. What about hydrogen? That's another obvious. Yeah. 1 what? 1 proton in the middle and an electron around the outside. Okay. All right. We're doing all right. So the important bits here, of course, are the electrons around the outside, aren't they? And we're familiar with carbon and its 4 bonds from all the structures that we've drawn and from those modelling beads that we've used and, attaching 4 all the time. So carbon and hydrogen form the largest part of the organic repertoire, if you like. What else could we throw in? Oxygen, I suppose. What we got in the middle of oxygen? I think you'll find it's 8, yeah. 8 protons, 8 neutrons, and so the first orbit, sorry, or first shell will contain, and the second will contain, yep. Okay, so there's oxygen. The other thing that we're going to need in order to get to grips with these reaction mechanisms are some of the halogens. All right, now in group 7, you've got fluorine, chlorine, bromine, iodine, and the others are not really going to get involved, to be honest. What's the significant feature of atoms like chlorine and bromine? The electrons, but they are, that's the important thing, that group are 1 electron short of a full shell. All right. However many electrons you could get into that shell, they're 1 missing. Okay, so it could be 7 in there, it could be 17, it depends what you're looking at. So chlorine and bromine we will meet in this context, but I won't bother drawing them at the moment. So atomic structure, it's important, you know, to bear in mind those outer electrons, the valence electrons, if you like. The other bits that you need to remember is, well, one of the next bits, the principles of bonding between atoms. We've got various different types of bonding, haven't we, depending on what's happening to the electrons. But bonding always involves electrons and the type is determined largely by the electronegativity difference between the atoms. Remember that vaguely? If there's a big difference between the atoms, what sort of bonding do we get? Ionic, yes. So ionic is where you've got such a big difference in the electronegativity that the more electronegative atom will actually pull an electron, or more than one, away from the less electronegative. So, for example, sodium and chlorine would react together to form sodium chloride, ionically bonded, sodium ions, chloride ions, because there's a huge difference in the electronegativity. What's the other main type of bonding? Covalent, yeah. So the covalent option is about sharing, isn't it? But is it always about equal shares? No. So we've got our 2 options. We've got the pure covalent bond, which is what you'll find between 2 identical atoms, for example. So 2 chlorine atoms would be bonded together in a chlorine molecule by a pure covalent bond where the electrons are equally shared between the 2. The electrons spend the same amount of time around both of those nuclei. Alternatively, you get the polar, that's right. So the polar covalent bond is the one where electrons are not shared equally, and it's because there's enough of a difference in electronegativity to pull the electrons one way towards one of the atoms, but not enough of a difference to actually pull the electrons off and create ions. So polar covalent bonds are sort of in between. And there's a sort of it's a continuous scale, if you like. It's not just, you know, distinct characteristics necessarily. That there is a sort of complete scale of bond types, and I will come back to that at some point. The other thing that I wanted to put in here that I can't remember. Oh yeah, reactions. Just, you know, these are just reminders of things that we've been doing all the way along. Reactions, well, reactions are, well, about movement of electrons again, really. They're about making bonds and breaking bonds, although you have to break bonds before you can make new ones. So they're about breaking bonds in reactants and then making bonds in the products. And the bonds, of course, because they are electrons being shared or donated or received, then reactions are about the movement of electrons. All right? Which is why, as we come up to this idea of the curly arrows that I'm introducing is about looking at where the electrons go in a particular reaction. All right, so understanding where one electron might move to, or where a pair of electrons might move to, and why. All right, so it is, it is quite complex, but this is, just as a reminder, these are the things that you need to be reasonably secure on. All right, so reactions are about movement of electrons. Now, somewhere I've done some more work on bonds, but I don't think we need it at the moment, actually. Okay, so if we now just sort of, keep that ticking over in the background, we can start working our way through some of this. And I'm not probably going to write very much on the board, but just sort of pick odd bits of this out in order to sort of clarify. The first side here, I'm trying to think which is the sensible order to do this in. We start with the reactive sites bit, I think. I'm always tempted, I should say, to go sort of anti-clockwise with this. They don't number the boxes, so I don't think it matters particularly. So I'm going to flag up little bits of this as we work our way around. So if we have a look, first of all, at the box in the top left on reactive sites. Now, we've just looked at this idea, the first one there. We've got three separate situations that will identify reactive sites in a molecule. The first then, actually, I shall summarise this as we go. The idea of a reactive site in a molecule then is a matter of just identifying vulnerable areas where it's going to be easier to perhaps move an electron, to add one on, to take one out, to break them apart. And so, like I said, if you've got a big molecule, it's not just going to be anywhere in that molecule. It's going to be the particular bits that we can identify as being reactive sites, which is usually the functional groups. So first of all, we've got this option of difference in electronegativity, and you've got an example there of a carbon bonded to a chlorine atom, and the difference in electronegativity is such that carbon with an electronegativity of 2.5 and chlorine with an electronegativity of 3.0 is enough to make the electrons spend more time around the chlorine. So we get our slightly, well, what we would consider, a polar bond. So any electronegativity difference, in other words, is there a polar bond there? Because if you've got electrons spending more time around one atom than another, then it's going to be easier to move them. Right? If they're equally shared, then less so. It's a bit like a tug of war. If you've got two completely balanced teams pulling on a rope, it's harder to sort of disturb the equilibrium than it is if you've got one very strong team and a weaker team. You can easily pull the rope away from the weaker team. So the example that you've got there then, and it doesn't matter what you've got, but the example with the carbon and the chlorine, where you end up with your slightly positive charge over the carbon, slightly negative around the chlorine, means that because the electrons are spending more time on the chlorine side of that bond, then that's a reactive site. The second option we've got is there a double bond. Now, we met these last week, and this idea of the double bond, we'll come back to this in a bit because this is going to be important in the assignment. So a double bond, what we get here is the pi bond. they describe it here as a pi system. And so the way I drew this last week is pretty much how it's here, that we represent a double bond perhaps like that. But what this is showing us between the two carbons is two shared pairs of electrons. So if we were to draw that as a Lewis diagram, we'd have 4 dots in the middle there. Now, you can't actually have all 4 electrons spending equal time round the two carbons. It doesn't work like that. So what we actually have is the two carbons are joined in the middle by a single shared pair of electrons. So you've got 2 electrons here, and that is the sigma bond. I'll label this separately. And then the other 2 are found somewhere above or below, but nobody quite knows where. And that's chemistry for you. All right, so this bit, all right, those 2 are the sigma bond, that shared pair that are actually joining the 2, directly. But then this bit, all right, is our pi bond. So, yeah, it's not that they go round and round, it's just that you could find them anywhere. It's all a bit of guesswork, to be honest. So, obviously, that's quite vulnerable because, well, the pi bond is the vulnerable bit. The sigma bond isn't. That's quite strong. But the pi bond, you've got these electrons just sort of, well, they could be here, they could be there, they're floating above and below the, the central shared pair. Well, it's going to be quite easy to pull one of those away, or even both of them. So we'll be back to them because that pi bond is a very vulnerable area as far as electrons are concerned. And so, yeah, we can steal those away relatively easily. You then have the third option here, perhaps something that we've not considered anywhere in our bonding and other stuff. We've got this idea of lone pairs. Lone pairs are electrons which are not involved in bonding. So if you have a look at the example there, we've got a carbon attached to a hydroxyl group. And what we're being shown here, right, I'm not doing the bonds the same way as they are on this sheet. On the sheet, you're getting the little wedge-shaped bonds. Those are ones that come out of the paper towards you. Right? And the dashed lines are ones that go into the paper away from you. All right, so it's to give a 3-dimensional impression. Doesn't really work, does it? But if you've got an OH group here, I'm going to draw it slightly differently from the version on the sheet. You've got a shared pair here. You've got a shared pair here. All right. But the oxygen, if you remember rightly, back to the previous board had, all right, we've got, might be forming one of the bonds, all right, that one, and that one might be forming the other bond, but we're left with that is a lone pair and that is a lone pair. Okay, they're not involved in the bonding, but they're just sitting around, these little sort of negative clouds of electron presence. And so what we've got then, if we were filling in all the electrons around the oxygen, we'd have those 2. Now, they've not been drawn, they haven't included the other pairs in there, but what you then very often see as a diagram is a version of it that looks like this, with the lone pairs actually sticking out like that, and then put in little bubbles, almost like Mickey Mouse ears. And some of the bonding, the bead kits have actually got little plastic inserts that you can put onto the atoms to actually demonstrate lone pairs. Doesn't really work with the models that we've been using, but each of those then is exposing electrons, if you look at it, isn't it? So the first one, we've got electrons exposed out here, spending more time around the chlorine than the carbon. in the second one, we've got these electrons in the pi bond that are further away from the strong bond, so they're a bit vulnerable. And then we've got these lone pairs that are not involved in bonding, so you know they could be attacked and they could be part of a reaction. So this idea of reactive sites is you know, just a matter of identifying somewhere in a molecule where you know we're going to have these little vulnerable areas. Okay, I think if we go down to the box at the bottom left now, what attacks what is the next bit. We've got two types of substance that will come in and react with the reactive sites that we've just identified. So first of all, we've got nucleophiles, and then we've got electrophiles. Okay, now a nucleophile then attacks electron deficient regions, and that is a curly arrow that's showing. Right, let's add a bit more explanation to this. All right, if we've got our over here we've got nitrogen attached to something and it happens to have a lone pair, okay, drawn with its little Mickey Mouse ear around it. And then over on the right hand side we've got the polar bond that we drew back at the beginning of the reactive sites bit. So we've got our carbon and our chlorine, and although they've put a delta plus on there, they've missed out the delta minus there, just to remind you that the electrons were spending more time around the chlorine. Well, if they're spending more time around the chlorine, then the carbon has a slight positive charge, and you could therefore describe it as being electron deficient. It's not getting an equal share of the electrons in this bond. They are spending more time around the chlorine. So the tendency would be that the lone pair on the left here would actually attack this carbon here. And I'm not sure I should draw this in red, but I'm going to. The way that it would be drawn here, it would be to take our electrons. You don't have to actually even have them in a bubble and drawn as dots, but they will attack that end of the carbon to chlorine bond. All right, so that is a curly arrow. All right, it has a little curve to it. So this is a nucleophile. It's attacking an electron deficient area. So this is, oh no, let's not put another red one in, that'll confuse matters completely. Right, so that is electron deficient. Okay, it's lost its share in the bonding pair because they're spending more time around the chlorine. All right, so that's nucleophiles. Hopefully, you know, once we've got this side done, some of the rest should be a lot easier. The other option is electrophiles. I'm not 100% sure about the diagram on this. Electrophiles attack electron-rich regions. Oh yes, that's all right. They are taking electrons away from the electron-rich region. Sorry. Yes, I wasn't looking at it the right way round, really. The names, of course, tell you what's going on. Nucleo would be nucleus, electro, electrons. The phile bit means that they like these things. With the electrophiles, then, they are attacking an electron-rich region. Now, attacking that area means taking electrons away from it. And the example that you've got here, you have an NO2 plus ion. a nitrate 3 ion. It's not a terribly useful thing to be knowing at the moment. But obviously that in itself, because it's got a positive charge, must have lost, or it must be short of electrons itself. So not surprisingly, because it's short of electrons, then it will tend to draw electrons towards it. And so you could probably consider, you know, in terms of electrophiles, any positive ion is going to be likely to pull electrons away from an electron-rich area. The electron-rich area they've chosen to draw on here, I'm going to need to explain it now, I think. This hexagon with a circle in it, yep, somebody knows, that's benzene. Now, benzene is rather peculiar. Benzene is C6H. Right, well, I can draw it. Oops, lost a carbon. Okay, you've got a ring of 6 carbons, but they're not just joined by single bonds. You've actually got alternate double bonds, and all the rest of the space is filled with hydrogens. But the weird thing is, it doesn't just take that format, and it's because of pi bonds. Those double bonds there could be, you've got a sort of interchange between that arrangement and, that's better, done it properly this time, and the other bonds being double. All right, and that's this business about these electrons just not sort of staying as part of a bond between 2 carbons. And so what you actually end up with is written like that. And if you were to look at that sideways on, you'd have your carbon atoms in a, well, not quite a horizontal plane, would you? Because you can't join them sort of straight. So you'd have a slightly sort of, you know, zigzaggy sort of ring, where you've got single bonds between all the carbons and then a little cloud of electrons above and below. So this represents the pi bond that's formed here. All right. So this weird thing, then, it's benzene. And that is something that if I'd had the luxury of a bit of extra time last week, I might have thrown a little introduction to that in with the aldehydes and ketones. It's an example of what we describe as an aromatic compound. The aromatic compounds are usually based on the benzene ring. So this ring inside here just represents the cloud of electron location, you know, the cloud of electron probability, if you like, that you find above and below that ring. And so it's a very electron dense area. And so not surprisingly, you know, this positive ion here is going to see electrons pulled away from that electron-rich area. Okay, so that's the electrophile. It likes electrons, so it's drawn electrons away. So those words, the nucleophile, electrophile, just try to think which one we're using in the assignment. Oh, I think I've told you on there anyway, haven't I? I think it's electrophilic substitution, no, electrophilic addition. There's a lot of options, you see, and I don't want to do them all, so you've just got 2 on the sheet. And in fact, tomorrow I'm pretty much going to go through the ones that are on the sheet, but just using different atoms. So yeah, it should make life a lot easier. All right. So we've got, we know what's going to be attacked. We now have an idea of what's going to do the attacking. And so if we want to be describing a reaction, we can have nucleophilic or electrophilic, depending on where these electrons are moving. If we work our way around this sheet down to the bottom right-hand box there, the mechanism, well, we've got several things to consider there. The mechanism that's going to actually determine movements of the electrons will depend on certain things. First of all, it will depend on which way round the particles meet each other. Are they aligned appropriately? So first of all, best alignment or orientation of the particles. So you get a nucleophile there approaching that polar bond between the carbon and the chlorine. If that nucleophile approaches it from the carbon end, yes, you'll get a reaction. But if the nucleophile approaches from, I'm not sure what the difference is, I think I'd have put it completely the other way around. If it comes in from the chlorine end, it won't be successful. That's a very strange diagram, that one. So orientation of reactants. So yeah, if I was going to draw it, I would have, if that's your nucleophile, which up there we'd got, what had we got? Oh, a nitrogen with its lone pair. Just any old nucleophile will do. If it comes in like that, then yes, that's going to work. So you'll get, whoops, that's supposed to be a tick. All right, that will work. But if the nucleophile comes in, and I would have drawn it the other way round just to make it blatantly obvious that it's really hard to do it actually once you've done that, then that is not going to be a reaction. I could have done those in red, couldn't I? All right, that will work, but that won't work. You've got to have the attacking particle approaching the reactive site from the right direction. They're not just going to find their way around. So a lot of collisions between particles are not going to result in reactions. Yeah, we've got one quite interesting one tomorrow where once a reaction started, you get a chain reaction. Some reactions in that chain will actually restore your starting materials. So yeah, we have to consider sort of all options. All right, but I think that explains the orientation thing better than the diagram they've got on here. Electron arrangements, you know, what's available where, how many electrons are available for reacting, how stable is the intermediate, will the activation energy be high or low, will the reaction be slow or fast. There's, you know, a lot of other considerations, so I'm not going to try and explain those other considerations as well. All right, just to keep that considerations. All right, so we're not going to try and get too deeply into this, obviously, otherwise we end up trying to study the back of the sheets. Yeah. Yeah, I have no idea what most of that's about. No, biology degree. But I did chemistry in my first year. I was joint honours first year. So yeah, but now I've done. Oh, I've got an understanding. Yeah, but yeah, that's yeah. Organic chemistry is complicated. Okay, then you've got the box up at the top right. Will the reaction work? I don't think there's any notes I particularly need to sort of add to this one. But if you have a look, then you know there's some fairly obvious points. How good is the nucleophile or electrophile? You know, it's going to depend on numbers of lone pairs. It's going to depend on electronegativity. It's going to depend on all sorts of stuff like that. Good bases are usually good nucleophiles. So we've got an increasing nucleophilic activity going left to right in that little sequence at the top there. Water, ammonia, hydroxyl ion, and then an H- ion. Very unusual. It's a hydride ion. But you do come across hydrides, metal hydrides, and yeah, a little bit odd. How reactive is the site? So there is a sort of scale. So you've got that double bond there between a carbon and an oxygen, which we will call a carbonyl group. I thought you were going to jump in with that one. Yeah, the C double bonded to the oxygen there is carbonyl group. More reactive. That, you know, that exposure of the electrons in a pi bond is going to be more vulnerable than just a slight, you know, unequal distribution in a polar bond. So there is a difference. You know, the sites are not always as reactive as others. Can the attacking particle get in? Is there steric hindrance? Well, we know steric is like stereo. It's to do with shape. All right. So is there shape hindrance? Is the shape stopping the particle getting in and reacting? So, for example, that one that you've got there with the hydrogens attached to the carbon has got much less in the way than the one that's got me attached to it. Me would be short for methyl. Right, it's a methyl group. But yeah. Putting Me there, just you know, shorter than putting CH3. The strength of the bonds is also important. How easily do they break? For example, you've got a bond between a carbon and a bromine atom at 276 kilojoules per mole. It's going to break more easily than a bond between a carbon and a chlorine at 338 kilojoules per mole. Simple as that. You know, that takes us back to our bond energies. This is why this unit fits together as it does, you see. The little bits and pieces I put in are supposed to just about knit together. And then you've got things like, you know, what might actually be leaving a reaction. How stable is that? A leaving group is an atom or group of atoms that leaves a molecule to make way for an incoming group. So H2O, which is nice and stable, of course, is going to be much better option than a hydroxyl ion that's got that negative charge on it. All right. So when we're thinking about organic reactions, we've got to take a lot of things into consideration. Now, you don't have to memorize all this, but it just means this sort of brings the whole unit together, because it brings together that understanding the atomic structure, understanding bonding of different sorts, understanding what reactions are. You know, anybody would think I'd designed it like this. All right. Okay, that's the first side done. We are not going to take the same amount of time on every single side here, but it is a bit of a slog to get this clear. And like I said, there's no easy way of doing it. It is just a matter of you know, working through the theory. Okay, the second side, I don't think this is going to take us long because I'm not going to explain every little bit here. But reactive sites, we now know what we mean by a reactive site in a molecule, right? It's not the hydrocarbon chain. It's going to be the bit that sticks out somewhere, the functional group. The reactive site is likely to be, you know, the carboxyl group or the carbonyl group or an alcohol group or something like that. So we know what we mean by a reactive site. And they give us a bit of clarification on that in that box in the top left there, functional groups and reactive sites. The thing is, of course, functional groups in themselves can be quite big, so somewhere within the functional group will be a reactive site. It's not the whole thing. So you've got some examples, and I will just write a little bit up as I go. Functional groups and reactive sites. So this at least partly goes with the recording, at least. You've got the electron deficient and electron, well, they described it previously as electron rich, didn't they, I think? Yeah, electron rich. Electron excessive is a rather odd sort of description, and I would prefer electron rich, really, as a description. But you have these two types of area. So you've got your that versus that, really, as the first sort of comment. So this one is electron deficient, and this one, of course, is electron rich. I didn't need to write electron out every time. I could just put E minus. And of course, where you've got one, you'll have the other. Yeah, so that in a polar bond, you know, you're going to have both. So which part of that is going to be attacked? Well, it will depend what sort of reaction, won't it? All right, because if you've got, you know, if you think back to where we were, nucleophiles attack electron deficient regions, so this bit, whereas an electrophile might attack the electron rich region. So a nucleophile, I'm getting sidetracked now, so that, oh dear, that was a bit messy, and then the electrophile will attack that bit. So this means that, you know, you've got, if you've got a polar bond like that carbon joined to the chlorine, where you've got more electron time around the chlorine than you have around the carbon, then you've got two potential reaction sites within that. You've got this bit and that bit, right? The electron deficient bit and the electron rich bit. It depends what's coming in to do the attack. What else have we got here that's, I'm not sure which way round to actually do these. Classifying organic reactions down at the bottom. We classify, first of all, depending on the type of reagent being used. Actually, this is quite a useful bit because this will help us, because you've got a lot of possibilities and we're only going to do 2 of them. All right, which you should be immensely grateful. So classifying reactions. First of all, we've got to decide what the incoming reagent is. Is it a nucleophile or is it an electrophile? So first of all, you've got electrophilic, I don't know why I've put it that way around particularly, versus nucleophilic. So that's the first option. Right. But then we have to look at what's actually happening to the organic molecule that's being attacked. And you've got a list of, I think, 3 options here, really. We've got the option of addition. Now, you can add an incoming atom. If you've got something you can add it to, and typically a double bond will provide you with the wherewithal to add. So the first example we're going to look at will be an addition. No, the second example is an addition that involves a double bond, so that you can use the spare electrons in that double bond, if you like. So that makes a bigger molecule. You can have elimination, where you remove something. We're not going to do any elimination ones. And the other option is substitution. That's going to be the first one that we look at as a substitution. Substitution won't be electrophilic or nucleophilic. It's just substitution. We then have, there are 2 other boxes on here, reagents. I'm not going to spend time explaining that. But the reagents will be classified as electrophiles or nucleophiles, depending on, you know, whether they've got lone pairs or what have you. And then down at the bottom, we've got reaction mechanisms. And this is where we're heading to. All right. Now, a reaction mechanism is always drawn in a particular way, and you have a series of 3 labelled diagrams in a reaction mechanism. You've got a before, a during, and an after. All right. Now, the temptation to draw anything else in between, you know, no, you don't need any other steps. Or the temptation to miss a step out, no, you have 3 steps when you're drawing a reaction mechanism. So that's going to be where we're sort of heading to, and looking at the curly arrows. So reaction mechanisms. All right, so you have 3 diagrams. basically before, during, and after. All right, so, you know, beforehand it's just your two reactants, you know, minding their own business, no electrons moving anywhere. The during bit shows the movement of the electrons. So the during bit is where the curly arrows are going to come in. And then after, oh, what are we left with? All right, so the curly arrows bit is, it's not, well, it's not only in the during bit, but the, you know, that's where we're actually showing what's happening. And then you'll see that the next page is all about drawing mechanisms. Yay. So electron rearrangements and curly arrows. Right, I think I'm going to introduce you to Jim Clark's bit on curly arrows, which I have stolen heartlessly off his website, but I'm telling you it came from there. Some of my sheets I do actually say taken from Chem Guide, because I think that's only fair, to be honest, but the yeah, I haven't done on this one for some reason, but this is where it comes from. So okay, so you've now got two sheets that explain to you how you can draw these reaction mechanisms between electron, well, you know, showing the movement of electrons using the curly arrows. The sheet that we've just been using, I think if we start with that one and then divert to the Chem Guide one to sort of clarify, because we've got several examples on the drawing mechanisms bit that are worth looking at. We know then that we've got a nice clear statement at the top of that the first box on there where it says electron rearrangements and curly arrows. During a reaction, bonds are broken and made. Yay, you know, something that we're familiar with. Bonds consist of electrons, and so during a reaction, electrons are moving. Well, fancy that, you know. Anybody would think I'd started with that this afternoon. So what we have are three options for the electrons. They can be sigma pairs. Now, the sigma pairs, remember, these are the ones that are shared equally between a pair of electrons, sorry, not necessarily equally, and not electrons, shared between a pair of atoms. So we've got two carbon atoms joined together there, an electron from one of them shown as a cross and a little circle for the other one, which is always misleading, but we just show that as a single line. So anywhere where you've got a single line representing a bond, that's a sigma bond. It's a shared pair of electrons, a single pair. The pi pairs, we have this rather odd example, you know, this odd situation, I should say, where you've got a sigma bond between the two carbons, but above and below we have another pair of electrons just sort of turning up. They could be both on one side, both on the other side, one above, one below. It's just a, you know, an area of probability where you would find them, but that's always just drawn as the two lines, the double bond. And then you have these lone pairs, which are something that we haven't really come across before. And where it's drawn there with the nitrogen with the two little circles, that's not really something that we do draw very often, to be honest. Although for a Lewis diagram, you would. Now, the things that can happen are that the pairs of electrons change from one kind of pair to another. And this is what these curly arrows are showing. All right, so you've got that first one. A sigma pair changes into a lone pair. Right, how to describe what's going on there. During a reaction, if we've got we've got our hydrogen and our chlorine, where you've got because these are not organic examples, obviously, right? Lone pairs here. The hydrogen's got one, and the chlorine's got one, and they're in that bond. And what that arrow is showing on that diagram there is that both of these are becoming pair on there. So the way that that's drawn is, all right, we've got these again. They're a bit time consuming. This line represents those two dots. What I've done here in this upper diagram is to repeat myself, really. The two dots and the line mean the same thing. So you only need the line to make the implication that there are two dots. And so the curly arrow on here shows that those two electrons are moving to become another pair on the outside here. So we end up with all these. Now, the problem is, of course, that now makes our chlorine negative. So you've got a chloride ion, which also looks like a little flower. All right, so that's what this is representing. That's rather an over-enthusiastic arrow there. The problem that you will come across is, how are you going to do these in your assignment? How are you going to do curly arrows? No. It's amazing, isn't it? With everything else, nucleophiles, electrophiles, substitution, curly arrows. Yeah. It's unusually simplified, isn't it? So that's one where you've got a sigma becoming, that's sigma to lone pair. Yeah. Oh, that's just turned into a hydrogen ion. So you'd have that. All right. Okay, but that would have been caused by something else that's not, we've not got the whole reaction here. That would just be hydrogen chloride splitting into its component elements, but ionizing. Actually, come to think about it, that's what will happen when you dissolve hydrogen chloride in water. And it ionizes and you get hydrochloric acid, don't you? H plus, Cl minus, I guess. All right, but that's taking our sigma bond and, turning it into a lone pair. But, that's now got a negative charge on it. The other options that we've got here, I don't want to sort of keep going over all of them, but you can have a pi bond becoming a lone pair. All right, so pi to lone pair. And what you've got there, it's not showing you anything attached to the oxygen there, but it leaves behind a sigma bond. All right, that's the important thing to understand there, that it's the pi pair, all right, that become a lone pair, and the sigma bond is still left behind. All right, so pi pair becomes lone pair, but the sigma bond, or the sigma pair if you like, let's say the sigma pair, unaffected. Well, not that they're unaffected, they've lost their other pair.
I'm confused because basically these lone pair, you don't have a negative charge then.
The lone pair, it depends what you've got to start with. What, that particular one, you mean? Yeah. What we've got there, we've got two electrons being transferred to our oxygen. The oxygen has already got one there. So you've got, all right, you're left with, if I put those in just to make it clearer, that we've now got, that could be the pi pair, could have gone there. All right, so they've made those, and then those were there anyway. Is that right? So yeah, why have we got? Yeah, why have we got the negative? I'll have to think about that. So we've got 8 round there. So yeah, I'm not convinced that we've got the negative charge on that one.
Electrical charge, P pair. So
Yeah.
we had a confused.
2, 4, 6.
Basically,
We should,
parallel.
yeah. As far as I can see, we've still got 8 round there, so I'm not certain that that's right. That may be a misprint. It may be me not getting it completely. But the
Basically, it shows us that there's a table with double bonds, and there are two traditional electrons,
yeah,
lone pairs.
yeah,
And next we've got one single bond
yeah,
and 3 lone
yeah.
pairs.
Because the third pair that we've gained was the pi bond. So the pi bond, what we did have was, here's our oxygen with that and that. This is 2,
To
and this is 2, yeah? So this is the pi bit, and they've come up here to form that.
so it's taken
Yeah, but it hasn't, has it? Well, that's not showing on there anyway. So, yeah, where on your sheet you've got a minus there, all right, I'm not convinced about that, because we've got 8 electrons around here. Yeah. I'll check on that. Yeah, it does look, actually, it looks right, because that comes up in the next one as well. I would have, well, because oxygen has 6, actually, I would have thought there'd be 2. You know, they would make it 2 minus. Luckily, we're not going to need that one. The other option, the lone pair into a pi pair, that's basically it going back the other way. So yeah, that's, you know, obviously that's that way, and then that way would be lone to pi. But what I've drawn on there is very messy and doesn't make a lot of sense. So let's not dwell on those too much. What I want to do is to sort of see what the curly arrows are doing for us, because I think looking at specific examples that we're then not going to use may confuse matters way too much. You've got an example middle left there, a simple acid-base reaction, and this, as you can see, it's not a you know, not a specific organic reaction going on here. And this is our, well, water and hydrochloric acid. That's interesting, because that's the one I was looking at, you know, as an option up there. H2O plus HCl. Now, you do get H plus and Cl minus, but in fact, that H plus can attach itself to the water. We actually end up with H3O plus, which is, yeah, not something that we're going to meet very often at all. I'm trying to think what they call that one. It's something like a hydroxonium ion, I think. No. Yes. But we're not needing that particular box. What would be more useful is the box on the right. Fish hooks and free radicals. Yeah, that's much more useful. I'm actually going to, I'm not going to remove that, but the fish hooks and free radicals. A fish hook is almost as technical as a curly arrow, because it's half a curly arrow. All right, if a curly arrow is 2 electrons, like that, then if it's just one moving, then you get half the arrow. That's a fish hook. Right. So a curly arrow is the whole thing. So that's an electron pair moving. Whereas our fish hook is a single electron moving. All right, so we don't always need to move whole pairs. We will sometimes, but you know, we might just need to move a single electron. This idea of free radicals. Now, free radicals used to be a bit of a, I don't know, they were almost part of sort of hippie type approach to, you know, food and you know, you've got to be careful to mop up your free radicals and all this sort of thing, and sort of thing that superfoods can do, and all that. And you know, there's a you know, a degree of sort of disbelief in them, but they do exist. Free radicals are a thing. All right, and a free radical is well, it's actually sort of like an atom, but it's an atom or a group of atoms, which the example you're given here is a really good one, taking chlorine. All right, now chlorine gas is Cl2, yeah? And the reason for that is that chlorine has 7 electrons in its outer shell, so it's one short of a full set, isn't it? So a chlorine molecule, let's draw it Lewis diagram style. And if we do it, actually this is exactly the same as it is on the sheet, isn't it? All right, there's our chlorine molecule. All right, so the one on the left has got 7 crosses representing its outer electrons. The one on the right's got 7 circles representing its 7 outer electrons. And here's our shared pair. Now, you can split those away from each other, okay? And you've got a rather peculiar little diagram there showing the the split occurs. I think it would be better to stick some colour on there between, ooh, no, they've done it the other way round, haven't they? I have to draw mine the other way round. Hang on. Right, we'll do it like that because then that's the same way. So the split actually comes there. So yeah, they end up just being atoms. So what? But what happens there, you can see, if you look really closely, the bond is being split and there are 2 fishhooks there. This one is showing the movement of that electron in the bond to the right-hand atom. This one is showing the movement of that atom in the bond to that atom. Okay, now what you end up with then are chlorine atoms. So why do we call them free radicals? Well, it's because they've got unpaired electrons and are consequently incredibly reactive. All right, so what you get out of this, all right, from this side we end up with our, all right, so that is an unpaired electron and is very reactive. This one, similarly, also has an unpaired electron. So these are free radicals, very reactive due to unpaired electrons. Okay, so the fishhook has just shown that you get an electron going to each atom. Now, that equal split of that bond so that each atom gets one of the electrons in the bond is described as being homolytic. Homo, same, so you end up with the same on each side. Lytic from lysis, for splitting. So this is a homolytic breakage, or whatever you want to call it. So this is a homolytic. You can get a heterolytic split, which would be where both electrons went to one side and none went to the other. Right, this one's homolytic because the 2 involved parties get the same out of it. Okay, the bit at the bottom about drawing mechanisms doesn't matter at the moment because we can now just sidetrack onto the chem guide bit. And this is all I'm going to do, I think, is just to get these curly arrows a bit clearer in the description. and then tomorrow we can take a journey through our 2 examples that we're going to need for the assignment, and then you can pretty much get on with it, to be honest. Yeah, I did tell you it wouldn't be easy, this. And it is, like I say, if this was lesson observation week, we'd have to do something completely different, because this is just not how it's supposed to be. But you can see that it's the only way to get through this stuff. So it's a good job it's right at the end of the unit anyway. Okay, if you look at the single sheet, the Chem Guide sheet, it is obviously, more user-friendly, and he just talks you through the process. And he does start by saying, curly arrows, and that's exactly what they're called. Right? You only use them for showing electrons moving about. They said electron pairs, but electrons generally. You don't use them for anything else. All right, so no curly arrows for anything else. This is what they do. This is their purpose in life. You have to draw them carefully if you're going to draw them at all. Now, actually finding a chemical drawing program that can accommodate curly arrows is not necessarily easy. I don't know if the ones that we were looking at for the first part of the assignment actually have curly arrows in them. Yeah? Yeah? Ah, right. Ah. Right, yeah. So, yeah, which one was that one? Is that yeah, yeah. Yeah, so it is possible then to get your drawing programs that will draw the curly arrows for you. The other fallback on this is a bit of a copy and paste off the internet, really. But obviously, if you can draw them yourself, then so much the better. So you have to start the arrow tail where the electron pair starts from. All right, it's got to be there as a bond, or if it's a lone pair, you've got to have that pair of dots. You've actually got to show the electrons there. All right, they can't just, the arrow can't be coming just from nowhere. And the head is where you want the pair to end up. All right, that's fairly obvious, but you've got to be careful with how I've drawn this. The fish hooks on that one. Yep, the tails are starting where the electrons start, and the end is heading towards the atom that those are going to. It wouldn't have mattered actually if the circle had gone to the left and the cross to the right, because an electron's an electron. It's neither here nor there. The fact they end up with a mixture of dots and crosses, it doesn't matter. He's given an example then, a reaction between ethene and hydrogen bromide. Now that's remarkably similar to one of the reactions that you've got to do for your assignment, as part of it. And you have a double bond there between the 2 carbon atoms. It doesn't look like that, but of course, the hydrogen is just sticking out. The bond there is between the 2 carbons, so you've got a sigma bond and a pi bond. And the arrow is starting at one of those lines because it is the electron pair in one of those bonds that moves. Right, so it's got to start at the line. And that you just have to decide which one is going to be your pi bond, all right, and then the other one isn't. So the bond there, it's just a pair of electrons that forms the pi bond. They move and they form a new bond with the hydrogen bromide. But at the same time, you've got the pair of electrons between hydrogen and bromine moving down to the bromine atom. We will talk through this whole mechanism, don't worry. We really are just looking at what the curly arrows are showing here. So we've got 2 curly arrows involved. One where you've got the pi electrons moving from the double bond in the ethene, and one where we're showing the bond between the hydrogen and bromine, that pair moving to the bromine. Now, if they've moved to the bromine is now, not going to be bonded to the hydrogen anymore, and that's the way that the story will go. The hydrogen, on the other hand, will get attached to the ethene, as was, by that pair of electrons that's moved out from the pi bond. So that's what's happening. So the electrons are forming new bonds, and he's got over that side, on the left-hand side, you don't have to draw the pairs of electrons in the bonds as two dots. You could put the dots in as well if you wanted, which is what you find that I tend to do when I'm trying to explain stuff. So if we go back up the board, oh no, it's previous one, wasn't it, where things started to get very confused. What I was trying to explain, you know, using the dots and the line, and I had a better one than that, I think. No idea where now. This is probably the one, yeah, where I drew them here and here. Yeah, my tendency is to say, well, this bond, this line represents the two dots anyway. So, you know, I'm overdoing it by, that's almost showing a double bond, isn't it, really? But you can put the dots in if you find that it makes your description clearer. And so if you have a look at the one on the left there, it's shown the pair between the hydrogen and bromine moving to the bromine. All right, so the arrowhead from the ethene points between the carbon and the hydrogen. All right, that's the top left carbon and the hydrogen that's attached to the bromine. That's what he means, because that's where the electron pair is going to end up. Those are the two things that are going to end up bonded together, which is shown actually down at the bottom right-hand corner of the page. The second thing that happens in this reaction, and it's a little bit difficult to do this without having done this reaction, because this is obviously what we're doing tomorrow. Once you've had that part of the reaction, what you're left with is the pair of electrons that formed that pi bond in the ethene then form a bond with the hydrogen that was part of the hydrogen bromide. You're then left with the bromine on its own, but the bromine has gained a pair of electrons where it actually only had one before, so it actually ends up with a negative charge. Now, because the electron pair from the pi bond has moved over to the left, of course the carbon on the right-hand side of that bond has lost part of the electrons it was sharing in that pi bond. So that actually gains a positive charge. You end up with that rather curious effect down the bottom right. And you know, if I try and explain any more of this now, it's going to be fairly pointless. But the overall reaction is that from that hydrogen bromide, the hydrogen joins to the left-hand side of the molecule as it's drawn using the pi bond electrons, but the bromine will join to the right-hand side of the original molecule using the electrons that came from its bond with hydrogen, and I think I might as well stop, to be honest. Sometimes you can almost hear your words sort of just hitting the back of the room and coming back. They're not being absorbed by anybody. But I know, I think it always is the same. This is a very complex bit to finish up on, particularly given the speed that we go through everything and, you know, the amount of content that we're trying to cover. So I think we will, yeah, we will leave it at that. Yes, it's coming back tomorrow, but we will we will go through the two reactions tomorrow that you'll need for the assignment. We'll go through step by step, looking at where the electrons go, and then yeah, if you want any help with the assignment, including that bit, then that's fine. All right.